Okay, so today I thought I will again repeat what I did in the last class because you were not there. Probably without it, probably it will be difficult to understand what we have to do after that. So let me quickly recap what we did in the last class. That is something called law of averages, and then something called box model to find out the gain of some games. Right? Uh, so in the book, they start the discussion by discussing about an example, a practical experiment that somebody did. So what he did was he tossed a coin 10,000 times, and each time he recorded whether he got a head or tail. Right? So for example, he recorded as 1 and 0. And then at each step, then he has a total number of, right, after one step, how many heads up to that point, after 10 tosses, how many heads up to that point, and so on. So we can calculate. So let me denote by the total number of heads by the nth toss by Tn, right? So number of heads by the nth toss is Tn, right? So Tn can be anything from 0 to n in that case. So if you think that this coin is a fair coin, you expect head and tail to come with equal probability. Therefore, you would expect if you toss it n times, on average, how many heads do you expect? N over 2, right? Because the probability of a head is 0.5. Right? If you toss it n times, you expect n over 2 times heads. So that is called the expected number of heads, right? Expected number. Right? But the actual number that we observe will not be exactly n over 10. Right? So therefore, we can write down a simple model if you write down the actual number of heads as Tn, then Tn will be equal to the expected number plus or minus some number. Right? So that plus or minus number is called the chance error. So that is the chance error in Tn. So what we are going to look at in this one is what is happening to this chance error when n is increases. Of course, we expect that Tn to be going up always when you increase n, right? But what is happening to chance error is the important thing. So we will look at that. So at each n, because according to the data, not I actually somebody else did it. So we have a graph. We can see what has happened, and then also I simulate the same situation to see what happens if you did it again. So that is one thing we are going to look at. Tn, so chance error, we are going to look at the chance error. So chance error is equal to then the actual number of heads minus n over 2. Right? So you can calculate. So these people have calculated the chance error when, for example, they had n equal to 10. By that time, he had seen 4 heads, but we expect 5 heads by that time. So therefore, the chance error at that point is negative 1. So like that, at each step we can find out what the chance error was. Then we can plot the chance error, this value versus this value. Right? So that's what they have done it here. In the graph, of course, the scale is not in the correct scale, because 10 to 100 is here, then 100 to 1000 is in the same, right? But what we want to see is what is actually happening when n is increasing. Right? So this axis is the chance error. Right? So you can see that the chance error at the beginning it was going close to 0, but after that chance error was going up in this case. This was one experiment. Right? So that is what happened in that experiment when n goes to when n is increased. So at this point, they have done it 10,000 times. So that is the behavior of the chance error of the total number of heads when n increases. And then we also looked at the proportion of heads, right? So total number divided by the number of times that we total number of heads divided by n will give you the proportion of heads, right? So the proportion of heads is therefore I will denote it by Pn, that is the proportion of heads out of the total number of tosses that we have seen by Pn, by the nth trial. So that is then Pn is equal to Tn divided by n. Right? And then what is the expected value of Pn? Right? Pn, the proportion of heads at any n, we expect it to be half, right? 50%, right? At any point we expect to have 50%, but of course the actual observed value will not be equal to 50%. So therefore we can write down actual number of actual proportion of heads is equal to half, that is the expected value, plus again a chance error. In that case the chance error of Pn. So the chance error of Pn is therefore equal to this thing minus half. So that we will look at that quantity also, what is to see what happens to the chance error of the proportion. So this is what they saw about the chance error of the proportion. This is the chance error of the proportion, that is the percentage of heads minus 50%. That is what they have calculated as a percentage, or you can calculate it as a proportion minus 0.5. Both will have the same shape. What you can see is these two are different, right? Earlier the total, the chance error in the total was increasing as n. Right? But here we can see that the chance error is coming close to 0, right? Chance error is coming close to 0 when n goes to infinity. Right? So that is the behavior. So this is only coming from 10,000 trials, one time they have done it. So I wanted to see again, I wanted to do this thing again and again and again several times. Do it 10,000 times and see what kind of line or graph we get. Do it again 10,000 times to see what kind of graph we get, and so on. So therefore I simulated the data. I can just assume that you have a box of zeros and ones, just 1 0 and 1 1, or maybe 50% zeros and 50% ones. It's like drawing tickets from that box, right? So I can write a small program and then simulate this thing. What I did was I did it 100 times, right? I took or flip the coin 10,000 times, I look at the graph, and then I do it again 10,000 times, look at the graph in that situation. So when I plot all those things, right, this is what I saw. Actually, this is not the error. What I have look at here is this one is the actual Tn, total number of heads by 10,000 tosses. So actually these lines are going to be very, very close, right? But you can see something at least. What can you see here? Right, this is the expected, right? Expected number of heads is equal to n over 2 always, right? And if you have done it n times, then the expected number of heads is n over 2. So this middle line here is y is equal to n over 2 line, right? With a slope half, right? So you can see that these curves, like what you did earlier, what you saw earlier, are going to be sometimes maybe all the lines are going to be above the line where this n over 2 line, or maybe some of them are all below the line, or maybe some of them are going crossing like that. But what you can see here is the dispersion. For example, if you look at when n is equal to 1,000, Tn was between these two lines, right? For example, here if you consider 1,000, right? So Tn was in this interval. When n was 10,000, Tn was in this interval. Right? So you can see that the possible values of Tn, or the range of Tn, is increasing. Range of Tn is increasing with n. Right? What I have done here is actually the error, chance error. right? So that is actually Tn minus n over 2, chance error. So you can see that, right? So this is now n over 2 line becomes 0 line now, right? Because expected error is equal to n over 2 divided by n over 2. So that is 0. So these are the chance errors. Again, you can see that the chance error is also increasing. Earlier we saw something like this, one curve only. Now you have 100 possibilities. Right? So you can see that the chance error, when, for example, when n is equal to say 4,000, is going to be between this and this roughly, chance error. But when is equal to 10,000, the chance error can be anywhere here. Right? So chance error, the range of possible chance error is becoming large as n goes to infinity. Right? So earlier we had only one curve, now you are seeing all the possibilities, 100 possibilities here. Right? So that is about Tn. Right? So the range for Tn is increasing, at the same time range for the chance error of Tn is also increasing. That is the total number of heads. If you look at the same thing for the proportion, this graph is the proportion, this graph is the chance error of the proportion. So the expected proportion at any value n is equal to 0.5. So this is 0.59. So you can see that at the beginning, the chance error had a large kind of variation, but when n goes to n is increases, this is coming to 0.5. It's coming to the expected value. Right? The Pn value is coming closer and closer to the expected value of Pn. Right? And therefore, the error is coming closer and closer to 0. Error is coming closer and closer to 0. So that is the situation. Now the previous one is Tn, the total number of heads. This one is Pn, the proportion of heads. In this case, if you look at the proportion of heads is equal to Tn divided by n. But what is Tn actually? In this case, we are drawing from a box or maybe tossing a coin, but each head is denoted by 1, each tail is denoted by 0. So Tn is like sum of ones. Sum of ones. When you divide it by n, what you get is actually the proportion of heads, proportion of ones. Actually, that is equal to, in our usual statistical knowledge, that is the sample mean here. Right? You are getting numbers ones and zeros n times. All the numbers are ones and zeros. If you get the mean, that will be equal to Pn. Right? If you add all these numbers, you will get Tn. That is the number of heads, and then divide by n. That is the proportion. But in other words, that is the same as usually what we call x bar. X bar usually sample mean of those possible values. So what this picture shows you is that the sample mean, right? Sample mean I can denote by x bar n. When you have n observations, x bar n. When you have 100 observations, you can denote it by x bar 100, like that. So x bar n or Pn, both are the same, are coming, x bar n is coming close and close to the expected value of the x bar n. And therefore the error is coming close and close to the 0. So this phenomenon is what we call the theory of large numbers. Theory of large numbers. So that means whenever you take a sample of size n, for example, from a population, right? So this is when you're taking tossing a coin, it's like taking a sample from a population of zeros and ones. Right? Because we are taking with replacement, even if you have one ticket and 1 ticket, because we are taking the with replacement, it's like a large population with 50% zeros and 50% ones. So if you are taking a sample of 1 or sample of 2 items or sample of 3 items and sample of 4 items and look at the the behavior of the x bar at each point, you will see that x bar value is converging to the expected value of x bar when n is increasing. So that is what you call the law of large numbers, or sometimes some people call law of averages. Law of averages. So that means sample mean converges to the population mean. When you have zeros and ones, the population mean is 0.5. Right? So sample mean x bar or Pn, both are the same in this case, is converging to 0.5 as n goes to n becomes large. So that is what the law of large numbers is. So that is one example of law. That is one particular example when you are taking a population of with containing zeros and 150% each. Then you saw that sample mean is converging to 0.5. Right. So let's look at another example. When you are drawing a different box, let's see whether still this theory can be applied. So let's consider this box and assume that we are taking a sample of size n with replacement from this box. Right? So it is like assuming that when you are taking a sample of size n from a population with 1 over 6th ones, 1 over 6th twos and so on, it's the same, or taking sample of size n with replacement from this box. So again we will look at Tn, and in this case there is no point of talking about Pn because Pn can be talked when you have only two things, but here we will look at the sample average. Right? Tn divided by n is x bar n. I will denote it by x bar n. Right? So we will see what happens to Tn as n increases, and therefore what happens to the chance error of Tn. And also what happens to x bar n, sample mean, and the chance error. Right? So in this case, what do you expect the Tn to be when you have n items in the sample? Whenever you take one item from this, on average, what do you expect? You expect on average the average value of these numbers, right? Because in the population there are, for example, if there are 600 items in the population, there will be 100 ones, 100 twos, 100 threes to have this kind of thing, right? So therefore, what is the population mean in that case? Right? Let us assume, for example, or you can just consider this one also, 3.5. The mean is 3.5. So when you take one item from this box, on average you would expect that to be 3.5 on average. Right? So therefore if you have taken n items, then the total of those things on average, what is called the expected total sum, will be then 3.5 times n. 3.5 times n. Right? So you would expect your Tn, when you increase n, Tn to be going around 3.5 times n line, 3.5 times n line around this. So that's what we expect Tn to be behaving. Right? And then if you consider the chance error will be Tn minus 3.5 times n. Tn minus the expected value. So this is the expected value when you have n items, when you have taken n items. So we will look at those two, and this is what happened, right? It's a Lycova game. Right? The variation is larger than the previous one. In the box, we had only zeros and ones in that case. Now we have 6 numbers in the box. So you can see that usually, so this middle line is the 3.5 n line, right? So you can see that there are some. Again, I have looked at 100 possibilities, up to n equal to 1000 only I have looked at here. So you can see that again the variation of Tn increases with n here. Variation of Tn, for example, the possible values when n is equal to 5000 is from here to here. Sorry, this is 500, and this is 1000, 10,000. The possibilities are in a large range. Right? So the chance error you can see clearly again increasing. Right? Possibilities or the range of chance error increases with n. So that is about the Tn. If you look at the sample mean is again like in the previous case. Sample mean is converging to the population mean. Right? In this case, the population mean is 3.5. So here is the 3.5 line. 3.5. This is 3. So you can this x bar n is converging to this line as n increases. Right? And because of that, the chance error is converging to 0 as n increases. So this is what you call the law of averages or law of large numbers. Again, when you are taking a sample from a population, if you consider the sample mean will be converging to the population mean when you increase n. So, if your sample size is not that large, for example, if you are taking a sample of size 10, possibilities are x bar n will be around the population mean, but there can be a large variation if you do it again and again and again, 10 times. But if you do it 100 times, if you take a sample of 100 values, then calculate the sample mean, that sample mean will be more close to the population mean. So that's what the law of averages mean. Right. So theoretically, I have written it in a mathematical way, even though your book doesn't have this. So this is what the law of large numbers means. Let x n bar be the sample mean of a random sample of n observations. So I use this notation to denote this is the sample mean when you have n observations in the sample. Right? Suppose you are taking a population. Right? When you're taking a population, maybe it's a finite population. In that case, when you are taking with replacement, or if it is a very infinite or very large population, even if you take without replacement, both in this will be correct. This idea will be correct. But theory is just for when you are taking with replacement or assuming that the observations are independent. Then it says x bar n converges to the population mean. Population mean is denoted by mu here as n increases. Right? So theoretically it says when n goes to infinity, x bar n will be converging to the population mean. Right? So this means for large values of n, the observed average becomes a more accurate estimate for the population mean. Right? So that is the practical use of this. Usually when you want to estimate some population mean, you use the sample mean as an estimate. Right? But the theorem says if you have a large sample, then you can have a high confidence that your estimate will be more accurate than when you have a small sample size. Right? So that's why we said whenever you are estimating something, take a sample as large as possible, then according to this theorem, for example, it will be more accurate, right? On average, of course, right? Okay, so that is one part in the book, law of large numbers. And then the book discusses something called the box model to look at the net gain of some chance models, like playing roulette and so on. We can look at the total gain, again total, like in the previous situation, but total gain will be the sum of the amounts that we are getting, right, earning. So that will be the total gain. We can look at what will be the total gain, what are the possibilities of the total gain if you place the same bet again and again and again on the same number, for example. You can just find out what will happen, what are the possibilities and so on. Of course, in chance games, always there is high probability of losing than high probability of winning, but sometimes there can be rather larger probability of winning than what we expect also, but still it's less than 0.5 usually. So let's look at this example. So as I was telling in the last class, I was not very familiar with this roulette game. So anyway, so it has some this kind of roulette wheel. There are 38 places in the wheel. There are numbers up to 1 to 36, and then there are zeros, 1 0 and 2 0, 2 places. All the numbers from 1 to 36 alternatively red and black, and then 0 and 00 are green color. It's like black here, but it is green. So different types of bets can be placed, right? Somebody might say, okay, what they do is they turn this one, or then put a ball and then see where the ball goes and stops, right? So somebody might say, okay, when they start it, they say, okay, this will stop at a red one. So betting on a red, or betting on a color, or betting on whether the ball will be on the first 12 somewhere here, or the ball will be end up in somewhere here or somewhere here. So there are different types of possible bets, and how much you get on those things are also different, right? So let's look at, so this picture shows some different types of bets, how much you get and so on. So that's not very important to us, but let's look at one type of bet. So that is the red or black, that is betting on the color, right? You can say ball will be on the red at the end or on the black. So if you bet on $1 on red, say, and red number comes up, you get the dollar back, right? So if you bet $1, you get your dollar back, and you get another dollar from them, right? So that means you are getting $1 actually. Gain is 1, right? So if a black or green comes up, then they win, we lose our dollar. They get our dollar, right? So we don't get anything. So that means actually we lose our dollar. Right, so that is this kind of game here we are going to look at. So the question is, suppose you have just put a dollar on the red, and then this person called croupier spins the wheel. But suppose you play roulette 10 times, not only one, right? So you bet one time, and then again next time also you bet another $1, and next time also you bet another $1. Right? You want to see what type of gain can I get from this. So the gain will be equal to the sum of gains, right? The gain in the first time, gain in the second time, gain in the third time. Sum of those will be equal to the total gain, right? So what are the possibilities of this in one bet? What are the possibilities? You either win $1 or lose $1, right? So it's like drawing a box, ball or ticket from what kind of box? If you want to look at the gain, for example, you can look at the gain and the total of the tickets, the numbers in the tickets, when you are drawing from some box. Right? So what should be your box? The box should contain tickets, 2 types of tickets, representing positive $1 gain or losing $1. So the number should be then +1 or -1, right? So those are the numbers. But how many tickets should we have is the problem, right? So what is the problem? So we have to have a certain number of +1s and certain number of -1s.
+1s 18, -1s 20, 38 in total.
Or 38, so 36 red or black. So half of that is going to be red. So that is 36 divided by 18, right? So there is a 18 divided by 38 chance of winning in one game, right? 20 divided by 38 chance of losing. Right? So therefore you have to have a box where you have to have 18 ones and 20 negative ones. Right? If you have that kind of box, then you can look at what happens if you draw from this box 10 times with replacement. Right? And then look at the total. We are interested in looking at the TN in this case, the total. Right? So you will have to have 18 pluses and 20 negative ones. For example, some box with tickets written on those numbers. So we have to take 10 numbers with replacement, of course, to mimic 10 bits, right? And then after 10 we can look at what is the total of those numbers on the ticket. So that will be giving you one possibility of the gain. And if you now put again all these things, and if you do it again 10 times, you can find out another possibility of the gain, and like that. So in order to have some idea, I did the same thing using a computer. So this is what I got. Actually, I have jittered the points, because otherwise you cannot see the differences. Sometimes all the lines, some of the lines will be on top of each other. You cannot see differences. So what I did was I have jittered little bit the points. For example, this is one possibility, right? I think, yeah, it went like this, and this was the end point. At the end, the total was something like $1. This is 0. This is $1. So for that, right? That is one possibility. And there is another possibility. For example, you might end up here. If you end up here, then you have total gain $4. That is also a possibility. Right? Or you may end up somewhere here. So in that case, you may have lost a certain amount, for example, $6. Right? So that is another possibility. Right? So there are different number of possibilities there. Right? But you can see that the possibility, the range of possibilities is getting larger and larger when n is increases. Here, for example, you are playing only 10 times. If you play 100 times, this picture will be going like this. Right? So possibilities will be large. So we don't know actually what will happen because it's random, but what we can see is that the gain is going to be around 0, of course, but there's a higher chance that you will end up with negative value. For example, if you look at these 10 cases, this is one. Power. If you look at these 10 times, you can see that this is one time that there was a positive gain, this is another time, this is another time. I think there are 2 times here, so roughly like 5 times, because there's 5 possibilities of winning, and then the remaining 5% in this case of losing. But of course, that is just a possibility, right? But usually in this case, because there is a higher chance of winning, 20 divided by 38, winning the probability or chance in any game. So if you do it large number of times, if you simulate large number of times, you will see less number of positive gains and more number of negative gains. Right? But here roughly half and half in 10 games. This is just a coincidence. Right. So we will later look at how much is the variability. What is how do you find out the size of this variability? Possibilities. Calculate something called the standard error. We are here just looking at the possibilities only. Right. So that is the total gain. You can model it as the sum of n draws from a certain box. Right. Right. So that is another thing that we have to learn. Right. So let's look at another one example. If you bet $1 on a single number at Nevada roulette and that number comes up, you get $1 back together with winning of $35. So that's a very good right? You bet $1, and if you win, you win $35, right? So your gain will be then 35. You will have your dollar, of course, but that is not a gain. But in addition to that, you will have $35. If any other number comes up, you lose the dollar. You just lose your dollar. You, in this case, the loss is just -1. Gamblers say that a single number pays 35 to 1. So if you play that kind of game, then we say that's the amount that paid is 35 to 1. Okay, suppose you play roulette 100 times, betting $1 on number 17 each time. Right, so you are betting all the time on number 17. If number 17 comes, you get $35. If the number 17 doesn't come, you lose your dollar. That's the game. Right? Your net gain is going to be like sum of some draws from a certain box. So the question is, what kind of box? In the box, what are the tickets that you should have? How many tickets you should have to simulate this total gain? Right? That's the question. So you are going to look at what will happen after 100 times. So what are the possibilities? Either 35 win, that is, so you have one type of ticket is 35s, right? On the number, there should be 35. On the other one, -1. Right? Those are the two possibilities. But what are the chances of happening that? Chance of getting a $35 is what? Only 1 out of 38. 38, right? So 1, 35 and 37 negative ones should have be in the box. 135 and 37 negative. So you are drawing from that box 100 times, and at the end you look at the total of the numbers in the what you have got. So that will be your total gain, right? So in this case I have gain simulated. So that's what happened. Yeah. So what I have done is I have looked at only 10 simulations. But here up to 100. Right? So they wanted to look at the total gain after 100 bets. Right? So these are several possibilities. Again, I have jittered the points because otherwise all the points lines will be on each other. Right? So you can see that there is a possibility of somewhat high gains also, because there is a $35. No, whenever you win, there will be a large jump to the right, but whenever you lose only $1, right? So when you go down, it's going very slowly, but when you win, like here, your gain is going up, total is going up. But still, you can see that I think out of this 10 times, I don't know how many, but probably this side is more losses than more wins, I guess. Even though sometimes there is possibility of getting a large gain, like with very small probability. Out of all these 10, this is only one possibility, right? All the others, either wins are going to be very small here, just like $1, $5 or something, but with a small probability, right? But all the other times, more chances of losing certain amounts. Right? So these are the possibilities. For the TN, that is the total on the tickets. Right. So that's the end of this chapter actually. So in that chapter, what they discussed was the law of large numbers. That is, one thing is the average when you are taking a sample from a population. The sample mean converges to the population mean as the sample size increases. That is one thing that you learn. And the other one is, like, you can model the total gain of a chance game, like these are called chance games. The total gain in a chance game by using a box called the box model, right? It's like drawing a certain number of draws from a box with certain number of tickets with different numbers on the top, and you have to decide how many of each, and then the total gain will be equal to the total of the numbers that you get after, for example, n number, 100 times or 10 times. Right, so that's I think what we did discuss in the last class at the end. By the way, can we have, we didn't have the last week, can we have a test next week? Or do you need another week?
We'll have it next week.
It's possible, right? It's not going to be a tough one or something. I'll have some multiple choice questions probably. If you want, you can bring the book also. It's an open book. Open. You can have whatever the notes or your thing. But of course, you cannot use AI. Right. So you saw in the previous one, when you look at the possibilities, always when you look at the total is converging to the expected total, right? Proportion is converging to the expected proportion, right? So therefore, what we have to be able to get some expression for the expected value. We have already discussed that part actually, right? So usually the expected value will be equal to the expected value of total will be equal to the expected value in the box, numbers in the box times n. Right? For example, when you have -1 and +1, expected mean of the numbers in the box is 0. Right? When you are tossing a coin, that is the case. So the mean will, in that case, you had ones and zeros, not ones and negative ones. Right? Head is 1 and tail is 0. So two numbers are ones and zeros, therefore the mean is 0.5. So therefore the mean of n rows will be 0.5 times n. Right? 0.5 times n. When you have the numbers from 1 to 6, each one time in the box, then the mean of the numbers in the box is 3.5. So therefore the mean of the Tn, that is the total number of rows in n rows, will be equal to 3.5 times n. Right? So therefore that is easy. The mean of Tn is equal to the mean of the numbers in the box times n. The question is, what is the standard error? Right? Standard error is actually a measurement that is the same as the standard deviation of the all possible values. For example, you saw earlier when you look at the Tn is, for example, increasing like 3.5 times n, right? The variation was increasing like this, right? So at a given point n, you are interested in how much is the variation, right? We know its actual value is going to be around Tn, 3.5 times n, but how much is the variation? Right? So that is measured by something called the standard error. Standard error. That is the same as actually the standard deviation. Standard deviation of all possible values. For example, you do once and you do again, so your curve will be like this. So for example, as I showed you 100 simulations, you had different values. So therefore, it's actually measuring how much is the dispersion, right? Not actually the exact distortion. This will be roughly twice the standard error, right? So standard error will be roughly half. But anyway, standard error is a measure of how much the variation is. Right. So we will, in this case, learn a formula to calculate the standard error. So let's again look at this problem again, just to see what happens. Like in the previous case, previous example. Suppose you are drawing 100 numbers or 100 times from this particular box. So Tn is the sum of values at the nth row, right? After you are having n rows, total number of values that you have got is the Tn is the sum of xi. Xi is the value that you get in the ith row, right? So x1 is the number that you get in the first row, x2 is the number that you get in the second row, and so on. So if you add those numbers, you get the Tn. So the question is how large the Tn is, because Tn can be used, for example, to measure the the gain, total gain. So therefore Tn is an interesting quantity. So what is the amount value that you expect? That is what I mentioned a few minutes ago. That is the expected value of Tn, and it's not that difficult to understand. The expected value of Tn is going to be n times the mean of the numbers in the box. But the question is, what is the standard error is? So in this case, what is the mean? Mean is going to be the total number, the sum is 8, 8 divided by 4 is 2. So the mean is 2. Therefore, if you do it 10 times, the expected number of Tn is 2 times n. Right? So that means if you do 100 times, then you expect the total to be around 200. 2 times n. Right. But what is the variation is the question. Right. What are the possible values around that? So expected value is not difficult to understand, therefore I will just skip these things, just simple calculations. Right. So this is showing if you do it, if you take 100 simulations of 100 plays, right? So suppose you take 100 times from that box and look at the total at the end of the 100th row, right? So for example, this is what happened in one possibility. At the end, you end up here. There's another possibility like this one. So those are the two extreme